In Chapter 6, Section 8, we want to look at energy diagrams for multi-step reactions. We're going to look at a two-step reaction, but you could apply this to any number of steps, 3, 4, 5, 100 steps if that's how many were in there. But we're going to look at the energy diagrams for these multi-step reactions. All right. So previously we had looked at this reaction where the bond broke between A and B and simultaneously a bond formed between B and C. In this section, we're going to do that in two steps. And so in the first step, we're going to break the bond between A and B. That's going to form A minus and B plus. B plus is then going to subsequently react with C minus, and that will give us BC. So the bond formation, bond breaking and bond formation are going to happen in different steps. We will find that each one of these steps will have a transition state. Right? Between those two transition states, we will have an intermediate. The intermediate here is B plus. So when you have an intermediate, that is something that is not a reactant. It's not a product. But it's something that shows up in the mechanism. We will find that each step has its own energy barrier, in other words, its own activation energy, with a transition state at the energy maximum. All right. So now we want to look at the transition state for each step. Our first step, where we're breaking the bond between A and B, this is a heterolytic cleavage, so we have the neutral A-B bond here, and the electrons, both of those electrons go to A, so we get A minus, and then B plus. All right. So since we're breaking the bond, this is going to be an endothermic step. We'll find that all bond breaking is going to be endothermic. So this will be an endothermic step. We have a transition state. That transition state, remember the three steps for doing transition states: draw partial bonds, do partial charges, and then put brackets in the double dagger. All right, so there is a bond that's being broken, so we have a partial bond between A and B. Since A has a negative charge here and it's neutral to start with, that means there is a partial negative charge on A, and there is a partial positive charge on B because of the positive charge of our intermediate B. Our second step, where B plus reacts with C minus, looks like this. So here you'll notice that B plus reacts with C minus. Both of those electrons are going to come from C, and we will form a new bond between B and C. All right. Since this is bond formation, we'll find that bond formation is always going to be exothermic, so we will have an exothermic step here. And we'll find that the intermediate has partial bond formation. That's why we have the dotted line. The positive charge on B here, it's neutral on the product, so there is a partial positive charge on B at the transition state. And C has a partial negative charge. All right. You'll notice that the activation energy for this second step is really small. That tells us that the first step is going to be much slower than the second step. The bigger the activation energy, the slower the step. So we'll find that our first step is rate determining, and we'll see that when we put it all together, this will make more sense. So here we've put the two parts of the reaction coordinate diagram together, and we've combined them together in one big coordinate diagram. All right. The transition states are these maximum points, the maxima. All right. In between, we have the intermediate. In this case, the intermediate is B plus. So we form B plus in the process of the first step, but then we use it up in the second step. So that intermediate is always going to be lower in energy than the two transition states and higher in energy than either the reactant or the product. We'll see that each step has its own delta H. The first step, as we saw, was endothermic, and the second step was exothermic. We'll also notice that each step has its own activation energy. I pointed this out a minute ago. that the first step has a very large activation energy and the second step has a very small activation energy. That means that our first step will be the rate determining step. If we look at the difference in energy between the reactants and the products, that will give us the delta H, at least a very, very close approximation of the delta H for the overall reaction. And then, as I mentioned, since that first step has a larger activation energy, it is the slow step and therefore the rate determining step. So given what I've shown you, we're going to do number 46 on the in-class assignment. So we'll switch over here to number 46. Okay, so which points on the graph correspond to transition states? Again, the transition states are going to be the relative maxima, or the maxima points, so B, D, and F. Those are going to be our transition states. Which points on the graph correspond to the reactive intermediates? Well, those are going to be the relative minima between the transition states. So that would be C and E. How many steps are present in the mechanism? This is very easy. You just count the number of transition states, and that tells you the number of steps. All right. Label each step of the mechanism as endothermic or exothermic. All right, step 1, it's going up, so that one is endothermic. All right, step 2 is going down, so that one's going to be, I'll just put the number there. So step 1 is endothermic. Step 2 is going down, so that one is going to be exo. So step 2 is exo. And step 3 is also going down, so it is also going to be exothermic. All right, and then label the overall reaction as endothermic or exothermic. So we look at A going to G, and we'll see that since it's going down, overall it's exothermic. All right, so that is number 46. And once you kind of get an idea for how to do this, then we'll be able to put that into practice with some real reactions here in just a few minutes. All right, so in section 9, we want to look at kinetics and energy diagrams. And we've talked about this a little bit already, but kinetics we use, it's the study of reaction rates. All right. We'll find that the larger EA is, the slower the reaction is going to be. So between these two reactions, the red line and the blue line, we will find that the red one is a slower reaction because it has a larger activation energy. So that is the easy way to do this. All right. There are other factors that will affect the rate. We'll find that the activation energy will affect the rate constant. But there are some other things we can do to affect the rate itself. That is, if we increase the concentration of our reactants, this is something that you saw in General Chemistry 2, and we're going to look at it again. All right. If you have a higher temperature, that typically will increase the rate of reaction because it will be easier at a higher temperature. The molecules will have more kinetic energy. It will be easier to get up over that activation energy. All right, and then interestingly, delta G, delta H, and the equilibrium constant have no effect on the reaction rate. They only affect the equilibrium position. So the point of the reactant and our product, the difference in energy there, that will affect our equilibrium position, but not the rate of reaction. So it will not affect the rate of the reaction. All right. So we want to look at rate equations. And you've done rate equations in general chemistry, so this shouldn't be something that's new, but you probably need to review it. The rate law, or in some textbooks it's referred to as the rate equation, I typically will call it the rate law. It shows the relationship between the reaction rate and the concentration of the reactants. In order to get the rate law, you have to do this experimentally. You can't just look at the stoichiometry of a reaction. You have to look at it experimentally. The whole reason that we do rate laws, that we determine the rate of reaction and look and determine what the rate law is because it tells us information about the mechanism. It tells us whether we have a one-step reaction, a two-step reaction, a multi-step reaction, whatever. All right. So in order to determine that rate law, you have to measure the concentration as a function of time of either the reactants or the products and see how they change. Typically, your rate law will have this generic form where rate is equal to a rate constant K times the concentration of each reactant raised to the power of N, where N is the order with respect to that reactant. N tells us how many of those molecules we need to come together in that step. If we need 2 molecules of one particular reactant to run into each other, then N will be equal to 2. If we only need 1 of those molecules, then N will be equal to 1. Most of the time, we will find that N is equal to 1, but there are some unusual situations where N can be 2 or even a higher number, but I will caution you against trying to predict a third order reaction for reasons that I will explain in the future. We will find that fast reactions have large rate constants and slow reactions tend to have smaller rate constants. We will find that the larger the activation energy, the smaller the rate constant is going to be. All right, so let's look at a second order reaction. Again, we're going to be looking at A, B reacting with C minus to give us A minus plus BC. If this reaction is a one-step reaction, all right, so one-step reaction meaning a concerted where the bond is broken at the same time that the new bond is formed, then we will find that both of these reactants have to be present for this step to occur. Since both AB and C minus have to be present, we'll see that they both show up in the rate law. So anything that's in the rate law, anything that's in the equation for the rate determining step is going to show up in the rate law. All right, the order of the rate equation is equal to the sum of the exponents. And in this case, there's 1 molecule of AB, 1 molecule of C minus. And so each of those, the exponents are 1. And when you add those together, that gives us 2 overall. So this is a second order overall reaction. For a first order reaction, you just need one thing present. You don't need both present. So we'll see that it is possible to do that same reaction. AB plus C minus gives us A minus plus BC, and to do that in 2 steps. We saw this a few minutes ago when we were looking at these reactions. The first step is going to be the bond breaking between A and B, and we'll form A minus and B plus. And the second step is where C minus reacts with B plus to give us BC. Assuming that this has the energy diagram that we saw a few slides back, that first step was rate determining. So since that is rate determining, we will find that only the reactants in the rate determining step show up in the overall rate law. So it is required for C minus to be there to complete this reaction, but changing the concentration of C minus will not affect the rate of the reaction. All right, okay. And we're going to look at some examples of this here in just a bit. The final part of Chapter 6 is looking at catalyst and how catalysts change the rate of reaction. So we'll find that there are certain reactions that don't proceed unless we have a catalyst added to it. Here are a couple of examples. If we just take acetic acid and ethanol and don't put in any sulfuric acid or no other acids, we'll find that this reaction doesn't happen, or at least doesn't happen in any reasonable rate. But when we put the sulfuric acid in there, that speeds up the reaction tremendously. And so we're able to make ethyl acetate and water. Another example is hydrogen plus alkenes, in this case cyclohexene. If we put these two into a flask by themselves and let it sit there for 100 years, we will find that essentially none of it will convert into cyclohexane. And that is because the reaction is so slow, it has such a high activation energy that we are not able to do that reaction. However, if we throw in a small amount of elemental palladium, usually the palladium is absorbed onto activated charcoal, some carbon, so usually it says palladium-carbon, but the palladium is the stuff that does it. You can do hydrogenation of the cyclohexene to form cyclohexane, and this reaction happens quite easily. So without these, the reaction goes really, really slow. One cool thing about catalysts is that they don't get consumed in the course of the reaction. So catalysts are not consumed in the course of a reaction. You'll find that catalysts may get used in a first step, and then they are usually reproduced in a subsequent step. The way that catalysts work is this is actually quite important. Since it's regenerated, you don't need to have a stoichiometric quantity of the catalyst. So let's say we had 1 mole of acetic acid and 1 mole of ethanol, and we wanted to make the 1 mole of ethyl acetate. Well, we wouldn't necessarily need 1 mole of sulfuric acid. We might be able to do it with 0.01 moles, like 1% of the amount. Sometimes you can even have less, just depending on how efficient the catalyst is. Same thing with palladium. If you had to use 1 mole of palladium for every mole of hydrogen that you used, this would be a very expensive reaction to do. And so usually you can have millions of moles of hydrogen for every mole of palladium. The way that catalysts speed up reactions is that they lower the activation energy. Now, typically, when they lower the activation energy, they're going to change the mechanism overall. So sometimes you'll go from 1 step to 2 steps or 1 step to many steps, but you lower the activation energy. And so in doing this, you do change the mechanism of the reaction. All right. So let's look at numbers 48 and 52. Okay, so consider the following 2-step reaction. So here we've got this alkene reacting with HCl. We form this carbocation plus a chloride ion, and then that chloride ion reacts with the carbocation, and we get this. So how many bonds are broken and formed in step 1? So the number of bonds that are broken, we're going to break the pi bond and the hydrogen-chlorine bond, and we're going to make a new bond between carbon and hydrogen. So we're going to break 2 bonds, and I'll go ahead and list what those are. So the carbon-carbon pi bond. All right, so the carbon-carbon pi bond, and the HCl bond. So we're going to break 2 bonds and then form 1 bond. And the bond that we're going to form is carbon-hydrogen. All right. Now, would you predict this delta H to be positive or negative? Well, since we're breaking 2 bonds and we're only forming 1 bond, this is probably going to be an endothermic step. So I'm going to say, so it's probably going to be endo, so delta H is greater than 0. So delta H for step 1, we'll put delta H, and I'll put a 1 there to indicate that that's for step 1. So that is endothermic. How many bonds are broken and formed in step 2? Well, in step 2, if we look, there are no bonds that are broken, but we form one bond between carbon and chlorine. So no bonds broken. And one bond formed. All right, that looks a little ugly there, but that's formed. And that one bond that is formed is a carbon-chlorine bond. All right. Would you expect delta H for step 2 to be positive or negative? Since we're only forming a bond, we should expect that to be an exothermic step. So delta H for step 2 is going to be less than 0, and that is exothermic. All right. Which step is rate determining? Well, usually the step that is rate determining is going to be the step where bonds are being broken. If you have one step where there are no bonds being broken, and you have another step where some bonds are being broken, then the step with the bonds being broken is going to be the rate determining step. So step 1, because bonds are being broken. All right. It can get a little bit more uncertain if you have bonds being broken in each step. And there you may have to look at how strong the bonds are. All right. Now, draw the structure for the transition state in both steps of the mechanism. All right. So for our first thing, we're breaking this bond. We're forming a bond between carbon and hydrogen, and we're breaking a bond between the hydrogen and the chlorine. So the first step is to always go ahead and draw what is going to stay exactly the same. So that part stays the same. We're going to have a hydrogen and a chlorine. We're going to be breaking that pi bond, forming the bond between carbon and hydrogen, and breaking the bond between hydrogen and chlorine. All right, before I put the double dagger on it, let's get the partial charges. If we look here, there are no partial charges. And then if we look here, there is a partial, there's no charges at all here. And if we look at the intermediate, here we'll have a positive charge on the carbon and a negative charge on the chlorine. So we're going to put a partial positive on this carbon and a partial negative on that chlorine. Once we've done the partial bonds and the partial charges, then we can put the brackets and the double dagger to indicate that that is our first transition state. Sometimes I will indicate that by just putting a dagger with a 1 by it to indicate that it's the first step. So transition state for the first step. All right. Now for our next step, and I just realized that I put the hydrogen onto the wrong one. So I'm going to fix that. Just give me a second. Okay, so I paused that for a second so I could redraw this. All right, so we do have that partial bond here. We've got hydrogen, chlorine. All right, since the hydrogen is going to the top carbon, I wanted to put that in the correct location. All right, so this carbon down here is going to have a partial positive charge, and the chlorine will have a partial negative charge. So, sorry about that mistake. All right, now we want to look at the next part of this. So again, draw everything that is all the bonds that are present in both. So those hydrogens are there in both this and this. There is a hydrogen that is here. And then we've got a chlorine. We're forming a bond between carbon and chlorine, so we'll put a dotted line. And then we'll put a partial positive on the carbon and a partial negative on the chlorine. We'll put brackets around it, and then we'll put double dagger 2 to indicate that that's the second transition state. All right, if delta H overall is negative for the two-step reaction, that means it's an exothermic reaction overall. Draw an energy diagram illustrating all of the information in parts A through D. Okay, so first, we're going to have our first step, which is where we're breaking the bond. That's going to be endothermic. So our reactant is going to be here. All right, and it will go up in energy, and then we will get an intermediate that's right there. And then we will have a fast second step that has a fairly low transition state, and we'll have our product that is down there. And that this is our energy. So there's our reactant, our intermediate, and our product. Okay, and let's see. So our first step is endothermic, so it's going up in energy. Our second step is exothermic, it's going down, and you'll notice that overall the reaction is going down in energy. So I'm going to put little dotted lines here to represent where those energies are. All right, so this is delta H1. This is delta H2, and we'll see that it is exothermic. And then the difference here, that's delta H overall. All right. Our activation energy, and here I'll put, this is our transition state 1, transition state 2, and this is EA1. And then here, this is EA2. And you'll notice it's much smaller than the EA1. All right, and since we don't have numbers here, we can't like put the numbers on there overall. But that is our energy diagram for that overall reaction. All right, so here we've got a mechanism where we convert acetyl chloride into methyl acetate, and it is a two-step reaction. The first step, we're going to react this methoxide with the carbonyl, and you'll see that the electrons get kicked out there. And then in a fast second step, we lose that chloride and we form methyl acetate. All right, write the rate equation for this reaction, assuming that the first step is rate determining. Well, there's no need to assume that the first step is rate determining because it says slow. We know the first step is rate determining. So our rate is going to be equal to a rate constant, and we only need to look at the first step, and we'll look at each of the reactants that are in that first step. So I'm going to put CH3COCl, and that is to the first power, and then we'll have CH3O minus is our other reactant. Those are both first order, and since they're first order, we don't need to put ones there. They are implied if we don't put a number. All right, and anything that happens after the slow step doesn't show up in the rate law. If the concentration of methoxide ion were increased 10 times, what would happen to the rate of the reaction? Well, if you increase this by a factor of 10, the rate would increase by a factor of 10. All right. If the concentrations of both CH3COCl and OCH3 minus, if both of those were increased 10 times, what would happen to the rate? Well, if you increase this by a factor of 10 and this by a factor of 10, 10 times 10 is going to be 100. So the rate would increase by a factor of 100. All right. Classify the conversion of acetyl chloride to methyl acetate as an addition, an elimination, or a substitution. All right. So it looks like in that first step, we're adding it, but then we're losing the chloride. So we're essentially doing a substitution where we are replacing the chloride with CH3O. So this is a substitution. All right, and I believe that's it. Let me go back and see if there's anything left in the presentation. Yeah, so we have just a one last little thing talking about enzymes, and I don't have any questions on the enzymes, but enzymes are just really big catalysts. So they are biochemical catalysts. They're special proteins made up with sometimes dozens, sometimes hundreds, sometimes thousands of amino acid units. And they have very shape-specific shapes that are designed to do certain types of reactions. All right, so the reaction here is lactose reacting with lactase. So lactase is an enzyme that breaks the lactose into its component parts being galactose and glucose. If you try to do this reaction without the lactase, then the reaction just doesn't work very well. So it changes the mechanism of the reaction by doing this, and as I mentioned, the molecule fits into this little pocket. It allows the reaction to occur, and then our molecules can go off and be these monosaccharides instead of being this disaccharide. The enzyme is ready to do another one. In fact, it could be ready to do hundreds of them, thousands of them, maybe even millions of them. Enzymes tend to be very efficient and have lots of cycles. So it's not unusual for one molecule of an enzyme to do millions, billions of individual reactions. All right, that is the end of chapter 6. And so there we go.